Let's talk about doing linear regression using Spark and MLLib if you want to create a linear model of a massive data set. And I think we'll have a little bit more success with this one. What is linear regression? It's a very fancy term for a simple concept which is a common theme in the world of data science. People like to sound smart in this field, it seems. All it is fitting a line to a bunch of points, of observed points. So, for example, let's say I have a bunch of data of people's weights and heights. I can plot those on a graph like this and fit a line to it that minimizes the error between any given point and the line itself. And you can use that line to actually predict unobserved values. So, given this data set of people that I actually know the weight and height of, I can plot a line, and let's say I get a new person, and I know their weight, but I don't know their height for some reason. I can actually use this line to predict the height for a given weight. So usually the thing you're trying to predict is on the y-axis here. So let's say I have someone come along who has a weight of 120 kilograms. I can use this line equation to actually predict the height of that person, assuming a linear relationship. Obviously, not everything has a linear relationship, but if you eyeball the data, you can usually spot that pretty quickly. Why they call it linear regression or regression? Well, there is some weird historical reason that somebody told me once, but it's kind of confusing. It's really better thought of as just fitting a line to a bunch of points, or prediction would be a better word than regression here. How does it actually work mathematically? Well, it uses a concept called least squares, generally speaking. And the idea there is to minimize the error between the points and the line that you fit the points to. So, makes sense, right? Why squared error and not just plain error? Well, by using the squared error, we can make sure that positive and negative differences both get counted as positive. And by using the square in particular, big errors count more against it than small errors. So it's a good metric for actually making sure that the line fits your data points in the best way possible. If you remember back to high school, the slope-intercept equation of a line is y equals mx plus b, where m is the slope and b is the y-intercept of that line. Basically, what linear regression does is figure out m and b for you. And it can actually do that based on some pretty easily derived statistical qualities of your data here. And how the math kind of works out is actually pretty elegant, but I'll leave that for another time. However, there are more complicated ways of doing linear regression, and that is what MLLib chooses to do. So, kind of like ALS was a little bit overkill in terms of complexity for the problem at hand, Spark MLLib does it again with regression. They use a technique called stochastic gradient descent instead of what I just described. And yes, this is actually a good thing if you're dealing with multiple dimensions of data. So higher dimensional data is going to find contours to curves in a more robust manner. But it is a more complicated algorithm, and therefore it is more expensive to run. Granted, we're on a cluster here, so we can get away with it. For standard linear regression, maybe you wouldn't need a cluster at all. So I can see the point there, but there are some caveats to it that we will talk about in a moment where that kind of makes it a pain. Anyway, using it is actually fairly straightforward. So you just set up a linear regression with SGD object from the MLLib library. And you set up an algorithm and give it a bunch of parameters for its optimizer. And again, we have a bunch of magic numbers here, and there's not a whole lot of good guidance on how to set these effectively. You just kind of have to keep trying things until you arrive at something that gives you good results. And often, half of the work is just iterating on different permutations of these parameters until you find the ones that yield the most accurate results and the best predictions. So the way you do that in practice, you'll take this algorithm and train it, given a bunch of known data points. So, given you have, say, 100 people where you've already measured their height and weight, you use that as your training data to actually make this model. And then you can use that model to create a line that you will use for predicting new data points. So if you have new people where you know the weight but not the height, you would then test the model using that data. Now, the problem with SGD is that it doesn't handle feature scaling well. So if you're dealing with things that don't fit a normal distribution, where your data is not distributed in something that sort of looks like this, the SGD variation of linear regression does not work very well at all. It'll give you really wacky results, and you'll be wondering why. So in order to use linear regression with MLLib in the implementation that they have chosen, you first need to scale your data down so that it fits this range more better. So you want to make sure your data isn't very large and it has a good distribution and it's centered around 0. Okay, so to do that, you often need to scale the data down because in the real world, very few measurements are actually in this range and in this distribution. So, big downside of using SGD. So you do need to scale that data down and then scale it back up again when you're done to restore it to the proper values that you want to display in the end. Also, a limitation is that it will default to assuming that your y-intercept on the linear model is 0. And if you want to actually support y-intercepts that are not 0, you need to explicitly say set intercept true on the algorithm model. So let's do it. So for the example we're going to do, I've fabricated some fake data that tries to find a relationship between page speed on a website and amount spent. So imagine we're running some big online e-commerce website, and we're trying to figure out what's the relationship between the responsiveness of web pages and how much my customers spend. So let's try and build a model around that using some given data and see how well it predicts unknown data. Let's watch. All right, let's actually use linear regression in Spark using MLLib. So in the course materials, you'll find my data file, regression.txt, and you want to copy that into your course folder here, which I've already done. And if you examine the contents of that file, it looks like this. So it's just 2 columns separated by commas, and this turns out to be the format that MLLib expects for its input data, so it can read that in very simply. And this is just mapping simulated page speeds to amount spent. And again, I had to normalize this data down to a normal distribution range in order to get the algorithm to work properly. So you might say to yourself, wow, those are really small page speeds and really small amounts spent, but they've all been scaled down to fit into a range that the algorithm can handle. Again, big downside of SGD, but it's something you have to remember to do. Just scale it back up when you're done. So let's look at the code that actually runs it, and I've already imported that. So from the course materials, you'll want to import the linear regression.scala file into your project, which I've already done here, and take a look. So one thing I haven't talked about before is all the extra imports you have to do as well. So don't forget that. We are importing a bunch of specific MLLib classes that this script uses, including vectors, label point, linear regression with SGD, and squared L2 updater that we all use inside here. So we set up our context as usual, load up our training data. So what we're going to do here deserves a little bit of explanation. So usually with supervised learning techniques like this, where you're training an algorithm given a bunch of known data and then applying that resulting model to unknown data, you do what's called training and testing. So to evaluate the model, you give it a set of training data where you know the answer already. You know the labels for each data point. So in this case, we're getting page speeds as one axis, and we're trying to predict amount spent as the y-axis. So amount spent is our label in this case. That's what we're trying to predict. And to evaluate the model, we're going to throw some more data at it where we actually know the result, and we can compare the known result to what the model predicted. Okay, so that's what's called a train test. Normally, you train and test an algorithm using different slices of the data. So you wouldn't normally want to actually evaluate a model using the same data that you trained it on. But in this example, we're going to kind of pretend we never heard about that and actually use the same data for training and testing, just for simplicity. Now, in the real world, you wouldn't actually know the answers, so you wouldn't be able to actually evaluate the correctness of the final results. But same ideas apply. So to get this into MLLib, all we need to do is call labelPoint.parse on the training data and the test data, and that gives me back a RDD of labeled points based on that input file. Okay, so remember I had this comma-separated value 2-column data, and labelPoint.parse can automatically convert that into a labeled point object without any additional code. I am caching the training data because the algorithm may use it multiple times. Then I create my algorithm, linear regression with SGD. I set a bunch of parameters on it that I've tried a bunch on to find what works well. And then I run it, given the training data set. And at that point, I can create a model and use that to predict values on my test data. So what I've done here at this point, I've created a model that creates a linear model of the data that I gave it. I am now going to take that model and use it to predict values for just the page speeds of the test data. So what I'm going to get back are predictions that take the page speeds only from that test data, and then it makes predictions of the amount spent based on the linear model that we created. Okay. So what I want to do now is compare that predicted result to the actual result that was in that training data set. And that's what this next line does. It just zips in the known labels. See, testdata.map label. So that's extracting the actual answer that we got there and zipping it into our predicted results. So what I get back are these tuples of the predicted value and the actual value, so I can compare the two. And then I just go and print them all out. Make sense? All right. Let's do that. I already created a run configuration, nothing special about it, for linear regression. And we'll we'll run it. And there we go. So there you have it. Here we have our predicted results using our linear model that we created and the actual results. And you can see they're generally fairly close. It's a relatively small data set, and there's a good deal of random variation, so you certainly shouldn't expect it to be perfect, but the results are pretty darn good. So it worked. Yay. Woohoo. Now remember, you'd have to scale these results back up again because we scaled them down for the algorithm. Well, that's an exercise for the reader, and you can try that if you want. But if you do want to get your hands dirty with this, I encourage you to do so. So let me challenge you. Take this script to the next level. Instead of just printing out these results, actually compute the total squared error among the entire data set. So as you're printing out each line, keep track of the difference between the predicted value and the actual value, and take the square and add it all together, and then divide that by how many data points you had. That will give you what's called the R-squared metric of just how good this model is in predicting new values. Okay, so that will give you a number with which you can evaluate how good this model is. And once you have that working, what you can do is try different values here for the optimizer here, number duration, step size, and reg param, and experiment with them. See what effect they have on the final results and whether it affects your R-squared score or not. So if you want to get down and dirty and get your hands on and actually write some MLLib code yourself and fiddle with it, there you have it. See if you can actually create a metric of how good your predictions are overall by keeping track of the squared error, and see what those values do to it. All right, so go play with that if you will, and I'll see you in the next lecture.